Okay, we're coming in hot here with part 2 of chapter 12, Lotka-Volterra equations. Um, they're really just a small step beyond the population growth equations, the exponential growth equation in particular. We looked at last chapter, and they make sense once we move from alphabet soup into actual words. So read the chapter. If you kind of get this part and gloss over it, like don't stress about it. We're going to walk through it slowly. And then I think the figures they present on page 281, at first I looked at them, I was like, I don't get this. This makes no sense. But when you start to look at it, it makes a bit of sense. And then I'll try to provide some other resources for Lotka-Volterra predator-prey models, but it's a pretty foundational equation, so it's worth understanding the relationship of the terms. So with that, we'll walk through. I won't even go through these right now. We'll walk through them separately, so don't stress about that. If I can get there, let's see. Here we go. Okay, I'm going to cover this up right now. Ignore that. Exponential growth equation. Change in number over change in time, or change in number for given unit time, is a function of the number times the population growth rate. That's all this is. This is familiar. The amount with the change in number times change in the change in number for a given unit time is just a function of the number that we have in the population multiplied by the population growth rate. Sorry, I had a rough cut there. I went down this whole analogy that just fell apart at the end. So we discussed R and N, population growth rate times number of prey. Oh, that's not what I wanted to do. So now we're going over to this term. This is a negative term because this is the number of prey. Again, we're looking at the change in prey. The change in prey is negatively impacted by the relationship between the number of prey, predators, and capture efficiency. So if we, I can't really do it very well right now. Actually, we can do this right here. If we just look at N and P, all this is saying is that the likelihood that prey and predators are going to interact is related to the number of them. If you have more prey and predators, the likelihood of interaction is more common. If you have very few prey and predators, the likelihood of interaction is less. And so that's why it's a multiplied term. Number of prey times number of predators. So for a given number of prey, if we increase the number of predators, there's more likely going to be an interaction. If you're living in a field with 10 rabbits and 1 wolf, the probability of you being eaten on any given day is, say the wolf eats 1 rabbit a day, it's 1 out of 10. Now, if we put in the same field 10 rabbits and 10 wolves, each one eats a rabbit a day, the likelihood of you being eaten has now just gone way up. So those two terms interact with one another. And we're kind of assuming like not that much appetite limitation on the predators. And then the how efficient that predator is at capturing the prey is capture efficiency. So does the prey kill every single organism it runs into? Is it only 1 out of 10? What is the efficiency of that capture? And so in total, what this is saying is as number of prey or predators goes up, the change in prey population goes down. Capture efficiency is capture efficiency goes up, number of prey goes down. If capture efficiency goes down, number of prey goes up. So we can remove this box. And so now we've got our again, we'll go back here. Everything's normal, super happy rabbits in a field. Introduce a predator, and now this is balancing out the equation. So we've got the growth rate of the prey minus this predation term. So you can think of this whole thing as just a predation term. Just number of prey times predators times capture efficiency. The likelihood that you're going to be removed. So this is the overall rate of prey removal. And present. Yeah, we covered that when p equals 0. Okay. And then if there are no predators, this is all, if p is 0, 0 times whatever n is times a is 0. So we just go back to the exponential growth equation. Nothing different there. Now let's look at the change in predator population. So before we were looking at prey, now we're looking at predators. So the change in prey over the change for a given unit of time is equal to, let's think about how to break this one up. M and P, mortality rate. Maybe we'll start with this last part. This last part's the easiest, which is the change in predators over change in time is negatively impacted by M, mortality rate, times the number of prey. So whatever that natural mortality rate is, that's a negative term. So we can that's pretty simple. Change in predator over change in time is negatively impacted by the mortality rate times the number of predators in there. It's like a negative exponential growth. So we'll cover that up for now, because to me, looking at too many numbers just makes it harder. Maybe I'm making things more difficult. I don't know. Now we've got BANP. I don't know. BANP. So N and P we know. Prey, predators. Number of prey, number of predators. Predators need to eat prey, so it makes sense that their populations are that the predator population is dependent on the prey population. A, we already talked about, so that's the capture efficiency. So we're saying that the change in predators over the change in time is related to the number of predators and the number of prey multiplied by the capture efficiency of them, how well predators capture those prey. That all makes sense. And then B is a really funny term, and it makes sense, but to me it's a funny term. Efficiency of which prey are converted to predator offspring. Of course, B, that's, what else would be B? But the efficiency at which prey are converted into predator offspring. This is just saying, you can think of it as kind of like a growth term for the predators. So are they really efficient at taking calories brought in and turning it into babies, or does it require a lot of calories, many prey, to generate one new baby? And so that's all this is saying that the increase in population, or the change in population over time, is related to how well the predator takes calories, turns it into babies, times the capture efficiency the predator has on its given prey, times the number of prey, times the number of predators in the population. So it's just kind of think about it as the entire life cycle. Food, babies, death. That's all this equation is saying, is that the change in population over change in time is equal to food, B for babies. That's pretty easy. Let's do that. B for babies. Efficiency to which prey are converted into predator offspring, minus death. Food, babies, death. So all of life is in this equation here. And then if prey are absent, this whole thing turns to 0, and the population declines with the death rate, or mortality rate. Mortality rate would probably change if there's no food, but nonetheless, there we go. These are kind of funky. We'll walk through these. I think they work better on the graph, but I want to talk about the terms, and then we'll walk through the graphs. So zero population growth, isoclines. Cline just means gradation, iso meaning the same, meaning that zero population isoclines are a line at which zero population changes. It's a convoluted term to say zero population change line. They predict the change in predator and prey populations. Okay, for the prey population, decreases if the predator population is greater than R, which is the growth rate for the prey, divided by A, which is the efficiency. So population increases if the growth rate is greater than the catch rate. It decreases if P is less than the growth rate divided by the capture efficiency. A predator population decreases if the number of prey is less than mortality divided by our baby term, the efficiency at which prey are turned into baby predators, times the efficiency at which predators are, which prey are captured, the capture efficiency. And it increases if N is greater than the mortality rate divided by, again, the conversion rate of prey into baby predators times the capture efficiency. We'll walk through that and hopefully it'll make a little bit more sense here. So looking at this graph here, so all of these graphs are, the top three are the same. So the prey abundance increasing, which is N, less prey, more prey, less prey, more prey, less, more. Predator abundance, as predator abundance goes up, is on the Y. So here we're looking at the first one, RA, which is looking at prey population. The prey population decreases if P is greater than RA. If the predator abundance is greater than the rate of increase for the prey divided by capture efficiency. And then if the number of predators is below this line, prey increases. So you can think of this as the equilibrium line. Again, they call it the isocline. But here there's zero change in predator population or in prey population size. So with this many predators, there's no change in prey population size. If we have fewer than R divided by A predators, prey abundance increases. And if we have more predators than it's greater than R divided by A, then we have a decrease in prey. So this is just looking at the prey side. So depending on where you are on the y-axis dictates what's happening on the x. Now we can flip that around and look at how prey abundance impacts predator abundance. So here we have our isocline of M divided by BA, mortality divided by the conversion rate of prey into baby predators times the capture efficiency. If the number of prey is above that line, we have an increase in predators. That this B term is really working hard and they're making more predators. If we have less prey than M divided by BA, then the predator abundance decreases. How we get from that to cyclic nature is this graph. So this is combining both of these. And so I think it's useful to look at this and then go back to B and C. So let's start in the upper right-hand corner. And just ignore this wiggly business for a second. Just go to the upper right-hand corner for graph A. If you're in the upper right-hand corner for graph A, prey are going down, fewer prey. If we're in the upper right-hand corner for B, predators are going up, okay? So we go over here to the upper right. What's happening? Predators are going up and prey is going down. So we're increasing predators, decreasing prey. Okay, so that's just a combination of these two vectors. That's all it is. Upper left over here, declining predators. Upper left over here, declining prey. Bad for everybody. Upper left over here, bad for everybody. Lower left, more prey. Lower left, fewer predators. So prey are going up, but predators are going down. That's what's happening here. Prey are going up, which is this direction. Predators are going down. Lower right, prey are going up. Predators are going up. Prey are going up. Good for everybody. We like to be in the lower right here. Everybody's going up. Prey and predators. And so you can take that and move it like we did through time, which is all this is so looking at, for a given time, prey are increasing. There's a lag of predators increasing. Prey start to decrease as we get into the upper right. Predators are still increasing. And then we get to this corner here, upper left, everybody's declining. And then we move over here, and prey are increasing, predators are still declining, so we have an increase in prey, predators are still declining, and then we move over here and both are increasing. It's a complex figure, like sit with it for a minute and just think about, these are kind of compensation points, zero growth lines. Don't get too caught up on isoclines, but it's zero population growth for the prey, zero population growth for predators. And so looking at Locke-Volterra can tell us that predator and prey populations have an inherent tendency to cycle because the abundance of one population is dependent on the abundance of other. And there's these kind of lag effects. This is that experiment where they took, it was kind of funny because it's like two different mites. But there's a herbivorous six-spotted mite, and then a mean predatory mite that eats the six-spotted mite. They put some six-spotted mites in these little wells, some with oranges. There's either oranges, these are cue balls or something. And then they saw what happened over time. And so they put 6 of the six-spotted mites, which are herbivores. They're eating away on the the oranges. They let those increase, and then they release the predatory mites. And here's what happens. We start with the 6 herbivorous mites. They're eating away on their orange. They're super happy. And then we introduce a few of these predatory mites. And so they go off, and they start increasing numbers. The 6-spotted orange eaters are real happy. They're still growing. And then eventually they start to decline as the predators increase. Predators increase as prey are going down, and eventually they both go extinct. So it's kind of an interesting, mesocosm mite-based look at it. And then they increased habitat complexity and patchiness, and found that we would go through these boom and bust cycles. So here's prey are the light gray, and predators are the dark gray. So 6-spotted mites, the orange lovers are the light gray, and the ones that the carnivorous mites are the black lines. And so we kind of see the same pattern here, increasing herbivores and increasing predators, both going down, a lag with the predators. Herbivores going up, predatory mites going down, going up, the carnivorous mites, and then the same thing here again. So habitat complexity allowed them to go through these boom and bust without going all extinct. In the absence of habitat complexity, they're able to go extinct because effectively the predators are really good at catching all the prey, and they will eat all the prey, and then the prey population will go extinct, and then the predators will go extinct. But if we have microhabitat niches, different ways of dispersing, then we can think about the population more in a source sink model, and the overall population will sustain itself. In the absence of that, in a wide open plain where the carnivores can see all the delicious herbivores full of oranges, it's not looking so good. We'll talk a little bit. Now pain comes up a little bit later. So natural populations have similar dynamics. Mussels on the California coast can be driven to local extinction by sea stars, but small mussel larvae float on the ocean water and disperse to new habitats where they flourish until discovered by sea stars. And so here the prey the prey mussels might be locally extinct, but their larvae disperse out, and then they'll disperse in a new habitat devoid of sea stars, and they'll take over that habitat until a sea star shows up there, eventually grows and grows and grows. We get more sea stars to eat out the mussels, and this kind of like patch dynamics is happening up and down the coast. If we just had one patch, things would look different. But the coast is a continuum of little patches, and so the experiment of a single tray of 6 herbivorous mites and a couple carnivorous mites leads to extinction. But then when you move up from that small tray to an entire ecosystem, you have these little pockets flashing on and off all the time of mussel-dominated, sea star-dominated, mussel-dominated, sea star-dominated happening up and down the coast. And as a population, it's healthy. It's only when you focus on like the meter squared that you see these issues. Other factors are involved in population cycles. Food supply for prey can also fluctuate. Some population cycles be caused by three-way feeding relationships, effects of predators and prey on each other, couples with the effects of prey on the food plants on each other. Many factors can prevent predators from driving prey to extinction. Habitat complexity is a big one, and limited predator dispersal. Prey switching predators, so maybe they eat a certain prey down to very low numbers, where then it's no longer efficient to hone in on that prey, and so they'll switch to another prey. Spatial refuges, where predators cannot hunt effectively. Hidey holes, places to hide, and evolutionary changes to the prey populations. Plants are a good example of that, of coming up with defenses, other mimicry, other ways of defying detection. All trophic interactions have the potential to reduce growth, survival, and reproduction of the organisms that are eaten. Yeah. If the trophic interaction involves you being eaten, yeah, it's not good. The leaf-feeding beetle rapidly reduced densities of the klamath weed, an invasive plant. Here's the klamath. I assume it's klamath. European. It's in Europe though. Huh. Anyway, yeah, because klamath is CL, isn't it? I don't know. Whatever. I'm gonna call it klamath. The klamath beetle, the klamath weed, beetles. The beetles were able to eat it out and remove that invasive toxic species. Predators and herbivores can change the outcome of competition, thus affecting the distribution and abundance of competitor species. If a predator or an herbivore decreases performance of the top predator, the inferior competitor may increase in abundance. So this is a lot to unpack, and we'll talk about the rocky intertidal stuff a little bit later. And I hope to spend more time on this later because this is like seminal work in intertidal ecology. But Bob Payne, who was a UW prof for a long time, he passed away not that long ago. Maybe it's been 3 years, two or 3 years. I never got to meet him. It's actually one of my, it's a bit of hero worship, but it's like one of my biggest regrets, because Payne was my advisor's advisor. So my advisor was Paul Dayton, who graduated was one of Payne's early students. Dayton finished in 69 or 70. And so Payne did the study out on Tatoosh, which is just off the Macaw Reservation, where he'd go out and pull sea stars. It's a famous story, and there's a million videos and stuff about it. We'd pull sea stars from these certain areas and see what would happen. And in that case, what happened is when you remove sea stars, mussels take over and they fill up the entire space. They're 100% dominant. They outcompete everything else. When you have sea stars, they're keeping the mussels at bay, and that space is opened up for barnacles, limpets, all kinds of other stuff. And so in that ecosystem, the argument is that sea stars are keystone predators, meaning their predation of mussels improves biodiversity and ecosystem function. When you remove sea stars, it becomes a mussel-dominated system, all mussels all the time. This theory's been applied to like the kelp, urchin, otter thing we talked about earlier, where when you've got urchins, they eat down the kelp. When you have otters, they eat the urchins, which allows the kelp to flourish, which then increases this vibrant ecosystem. Same general idea. Well, it started here with Payne throwing sea stars off Tatoosh. That's a picture of Payne there with his pile of sea stars. It's actually from his New York Times obit. So carnivores can alter communities. This is another one. I guess it was 96. I thought it was a lot older than that. I don't know that much about these islands, but when they talk about just like introducing lizards on islands and see what happens, you're like, man, you can't do that stuff anymore. Not like romantically the good old days, but it's like, I think there's small barrier islands where maybe, I think it was the native range of these lizards. I don't think it was like, let's take these lizards to the Galapagos and see what happens. But nonetheless, they had 12 islands, 4 had lizards naturally, 4 had lizards introduced for the study, and 4 had no lizards. So they wanted to see what would happen when you introduce lizards to islands that were previously lizardless. And I'm assuming by this picture that that's what these things are. Like island is like a small mud flat that, you know, maybe gets a hurricane every few years and kind of gets rebooted. I don't know. So the introduced lizards reduce spider densities at the same level as on islands where lizards had occurred naturally. On islands with introduced lizards, 13 times more spider species went extinct than control islands. The density of spiders was about 6 times higher on islands without lizards. And so the introduced spiders started to drive, introduced lizards reduced density and then drove down, caused some extinctions as well. So these spiders are eating the spiders. Lizards are eating the spiders on these small islands. This Arctic fox example is kind of interesting. It takes it a couple steps further, as does the goose example coming up. So Arctic foxes were introduced in some of the Aleutian Islands around 1900. So a lot of introductions that happened throughout that range. This reduced seabird density by nearly 100-fold. Not shockingly, the seabirds are nesting in that area. They're easy prey for a fox. And then it kind of goes a step further, but it reduces the guano, bird poop, that fertilizes the plant. Guano, we often talk about salmon as this major mover of marine nutrients to the terrestrial environment, that they're so important because they're bringing all these nutrients up the river in their bodies, and then they die, and then the energy, the calories and the nitrogen from their body makes it into bears and all the invertebrates, and you can even measure that nitrogen in tree rings. So there's this like mass migration against the normal gradation of energy flow, which normally goes from the stream, follows the water, it's picking up energy, organic matter, etc., as it moves from the mountaintop to the sea. And so it's exporting energy in this form of nutrients and organic matter out to sea. Salmon reverse that. They go up, they die, they leave all this energy up in the streams. Well, guano is also very important, particularly for small islands where it could be the major source of nitrogen and, more importantly, phosphorus, which is frequently the limiting factor for a lot of plant growth. And so now the fox have eaten all the seabirds, so now there's no more seabird poop around. So what does that do to the plants? Here it says, with less guano, dwarf shrubs and herbaceous plants increased at the expense of grasses. And so grasses need more nitrogen and phosphorus. They're more nutrient dependent, and so those grasslands were maintained. They had a competitive advantage in a high nutrient environment. With a reduced nutrient environment, then these dwarf shrubs and herbaceous plants increased. So the introduction of foxes had an unexpected effect of transforming the community from a grassland to more of a tundra ecosystem. So pretty interesting to think about. And particularly that mechanism is kind of surprising, that it's like this loss of fertilizer, really. But it makes sense that in that system, that's your major source of nitrogen and phosphorus. Herbivores can alter communities. This is about the lesser snow geese that summer in salt marshes of northern Canada, where they feed on grasses and sedges. The plants are fertilized by goose feces, and they have rapid growth after low to intermediate levels of grazing. In the 70s, goose density is actually increased, mostly due to crop production at their overwintering sites, so corn, soybean, things like that they can eat during the winter. You drive around in the county and you see geese standing in cornfields. So they've benefited from this increasing agriculture. But at high densities, the geese completely decimate the vegetation, changing the distribution and abundance of marsh plant species. And so when they eat a little bit, it's good, but because they eat a little bit and they leave behind a little thank you gift in the form of nitrogen and phosphorus. But when they overstay their welcome, there's too many of them and they eat everything, then it's not good for the plant. So it's this the intermediate grazing falls into what I call the Goldilocks hypothesis, which can be used to explain pretty much anything, which is, too much is bad, not enough is bad, and just the right amount is good. And so here, none would be zero grazing. Zero grazing, and then this is grazing by the geese per minute. And the cumulative above weight in pp, grams dry weight per meter squared, net primary productivity is what that is. And so 0 is here after grazing for 15, 20, even 60 minutes. There's a benefit. So there's some grazing, but they're leaving behind nitrogen and phosphorus in the form of fecal matter. And that's starting to decline and presumably would go further if grazing was extended beyond 90 minutes. One example of that is this image of a marsh that's staked off to keep the geese out. And the geese have been all over everywhere else. I think that's even a goose in the back there. No, I'm not sure. They've been here. They turned which is goose excluder. It all used to look like this, and now it looks like a giant mud flat because the geese have eaten everything. So, not enough, not good. Too many, not good. Just right is good. The Goldilocks hypothesis, one of my favorites. It's actually a thing. I mean, it sounds like it's made up, but it's actually a thing. These golden apple snails, this is an interesting one which makes sense when you think about it mechanistically. So these golden apple snails were introduced. Most snails eat algae. This snail eats aquatic plants, algae, and detritus. And so, again, most snails are crawling along the bottom, eating algae on like rocks on the mud bottom, things like that. These golden apple snails really like aquatic plants. And so wetlands with high snail densities had few plants, high nutrient concentrations, and high densities of algae. I can skip this because I have it in the bottom here. The mechanism here is, imagine you can have a clear pond with a bunch of water lilies, a bunch of floating aquatic plants. what those floating aquatic plants are doing is they're absorbing nutrients from the pond, nitrogen, phosphorus, and they're floating. So they're blocking light from penetrating into the pond. They're intercepting that light and using it for photosynthesis. You remove those plants, now that light goes into the pond which now has increased nitrogen and phosphorus, and you get an algal bloom. An algal bloom then will decrease water clarity, increases turbidity, and because it's a big phytoplankton bloom, those phytoplankton will die and then create anoxic or hypoxic rather environments, low oxygen environments. So lots of algal growth is good until those things die. Then they become extra organic matter in the pond, which rots, consumes oxygen, and makes fish and things die. All of this is cascading because we've lost these floating plants, basically. The thing that's really impressive to me is how few of them it takes to do this. And so these two are log plots. We'll come back to that. So snail density. They did experimental plots, 0, 2, and 6 snails. And they're looking at water hyacinth. Those you've seen them before. Like they're white. They're little floaty guys. So snail density in numbers per meter. I'm going to start at A. Edible plant cover. So with 0, you've got 90, 75, 50, like a decent cover. You go up to just a few, 2 snails, 11, 12 on up. They decimate everything, which is super small numbers. So you have a few snails, they eat all of the plant cover, which if you have think about that, a plant cover of 90% means 90% of the sun's energy that hits that pond is absorbed by the water hyacinth, the floating plant, not by the pond itself. So now you've got a massive change in the solar energy that's absorbed by this pond. With that, when you've got lots of happy water hyacinth, reduced relatively low phosphorus, and relatively low chlorophyll. This is log, and this is log. So the difference between this and this is a lot. The difference between this and this is 10. And so even with a small here, with that small change in plant cover, we now have a massive increase in phosphorus. I mean, tenfold increase or more. I mean, if we're going from 30 maybe here to 1,000, that's a huge number. Here's probably, again, that's a log plot, so that's probably 2,000, 3,000. Chlorophyll values of 100, wow, micrograms per liter. That's a lot of chlorophyll. That's super green. Oceans are like down here. So that's a big change with a small addition of snails, but because they're attacking something that's really structuring the entire ecosystem, absorbing a lot of nutrients and absorbing a lot of light. Okay, that'll wrap it for 12. I'll try to find some other resources pointing towards the Lacovotera equations. The web exercises, web extensions in the book are good as well. So kind of play with those to get a better handle on it. All right, that'll wrap up 12.